want to talk a little bit about air resistance. How many of you have ever stuck your hand out of the window of a moving car and done the, I've got a fake wing hand, done the air resistance thing and experienced that? Some of you have. Air resistance is really tricky. I can only, since you don't have calculus, look at it in little snapshots, but we are going to talk about it a little bit. Those of you that have stuck your hand out of the window of a moving car, as you speed up, what happens to the force of air resistance? Does it get bigger? Does it get smaller? Or does it stay the same? Okay, it gets bigger. So one of the challenges with air resistance is as you're accelerating, F equals what? MA, and so there's going to be accelerations. That means air resistance is constantly changing. And so Sarah will basically be taking snapshots at certain locations. The air resistance right then at that moment was that. But a split second later, it probably changed because this object is accelerating. Also, you may have noticed that if you turn your hand sideways so that it's parallel to the ground, air resistance gets smaller. It depends on your cross-sectional area. And we just don't have the calculus and math skills to deal with a changing area and a changing force. But we'll start a little bit. What is air resistance? It's the force of air molecules bumping into an object that is moving through the air. Does air have mass? Yes, Finley?
Yeah.
Prove it.
It's made of particles that have mass.
Do they have mass? Well, let's see. I'm going to pause the video for a second. Air has mass. I convinced you with my little toy Airzuka because it applied a force. What direction? The direction of the force of air resistance is always opposite to the way the thing is moving. And that's, I think most of you kind of get that. If you're biking forwards, air resistance is trying to slow you down. Okay. Example 1 says, ooh, latecomer. We're back. So in our free body diagrams, when we're asking which way is air resistance pointing, what we're going to ask is, hey, which way is this object moving? Air resistance is going to be in the opposite direction. So unlike gravity, which was always down, air resistance, we'll have to think about it a little bit. Draw force diagrams for each of the following. Draw free body diagrams for each of the following. So we have 3 situations. A ball being thrown, and what I mean by that is while it's in my hand on the way up before it leaves my hand. Situation B is on the way up, right there on the way up. And situation C is on the way down, right there on the way down. Okay? Let's draw some free body diagrams. Although, Bryce, did they give me a picture? I'm going to label the picture rather than do a complete separate represent the mass as a dot. I'll be a little bit lazy, which technically isn't a free body diagram. But basically going forward, you're going to see if they give me a picture, I'll just label the picture with arrows and call it my free body diagram. I won't represent the mass with a dot. It's convenient. All right. While the ball is in my hand, what are the forces acting on it? Get the obvious one. Okay, let's put that in. Good old mg. What else? Let's ignore air resistance while it's in my hand. I agree there would be a little bit on the way up, but let's just ignore that. And I know that right away I'm kind of contradicting myself. Sorry? My hand? Sure. Let's call that, I don't know. I mean, you could call it a normal force if you wanted to treat my hand as a surface, but let's call it F throw. Ooh, F throw, bigger, smaller, or the same size as mg? Does it have to be bigger?
Yeah.
Okay, first of all, Finley caught himself. He said, well, it has to be bigger, otherwise it wouldn't be going up. Oh, accelerate, because again, Newton's laws tell us nothing about moving or going. They tell us accelerating. Look up. I will show you an example of where F throw is smaller than mg. Watch, 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 watch. Now I'll show you an example where F throw is bigger than mg. If it's smaller, it's not leaving my hand. Okay? So let's exaggerate it. I gotta be honest. That's, Emily, not the free body diagram that I was all that interested in, because today, for this section, we're talking about air resistance, and I chose to ignore it. Let's look at situation B. Once it's left my hand on the way up, what are the forces acting on it? Get the obvious one. Good. What else? Now, usually we'll ignore air resistance unless the question specifically says include air resistance. Next to part B, does it say include air resistance? Okay, so now that's why I skipped it for part A as well. It kind of, when it didn't mention it, we typically in physics say, okay, ignore it because it's messy. Which way is air resistance going to be pointing, folks? Which way is the ball moving? Opposite direction of motion. Down. I'll put it right beside. Mr. Dewick, is F air bigger, smaller, or the same size as mg? To be honest, I'm not sure. I don't have enough information. I'm assuming it's smaller just based on this little tiny throw that I did, but there could be situations where it's bigger. There could be situations where it's the same size. How can that be? We'll talk about that. C, on the way down. Okay. Madison, what are the forces acting on it? Get the obvious one. Yeah. Which way would air resistance be pointing? It did say include air resistance. Which way would air resistance be pointing here? Yep. Another word for air resistance, you'll sometimes see them call it drag. So you may see F drag, but air resistance. Okay. This middle diagram is interesting. I notice both arrows are pointing in which direction? So, example 2, I said, in example 1b, how can the ball be rising if all the forces acting on it are downwards? Have we screwed up? Joanna shook her head. She's correct. The free body diagram is right. So, again, I ask, how can the ball be moving up when all the forces are acting? Yeah. I agree with you, but I think we can even be simpler. This is something I'm trying to emphasize. Do Newton's laws tell us anything about moving? What do they tell us about? Okay, which way is this ball moving? I'm looking for a word that starts with the letter U. Is it speeding up or slowing down on the way up? So which direction is it accelerating? Look at your free body diagram. Do we have unbalanced forces down? Not a problem. Okay? But again, it's really tempting to start to think that Newton's laws, Paul, tell us something about the velocity of an object, which way it's moving. No. Accelerating? Yes! And again, this goes all the way back to last unit where Einstein said, hey, we got no experiments that can detect constant motion. We can only detect acceleration. So, Newton's laws tell us direction of A, not V. If you want to, you can write the word acceleration and not velocity, but hopefully by now you know I tend to abbreviate. So we're okay with that. It's not contradicting the laws of physics. Good. Ooh, Jada, in example 3, it says, if the falling ball is speeding up in this one, write a net force equation. If we're speeding up, I guess that means we're accelerating in which direction? I'm looking for where it starts with letter D. Who's winning? Who's losing? Equals. Yep. That's the generic template that I can give you. Winner minus loser equals MA, and you can adapt it for whatever. Mr. Dewick, why did you say is speeding up? I had to tell Jada that, otherwise she can't answer the question. Because it could be slowing down like a parachute, would make you slow down, or it could be exactly balanced, and that means not speeding up or slowing down, in which case it would be mg equals F air. So that's why I had to include that little phrase, it's speeding up, because Newton's laws tell us acceleration. Okay, good. All right. Suppose the ball in example 2 has a mass of 2 kilograms. If air resistance is 5.2 newtons, what's the acceleration in situation B? Okay. In situation B, I've scrolled down, but you have it in front of you. Which way are we accelerating? Which way must we be accelerating? Look at the picture. Which way must we be accelerating? Down. Which way is the winning direction? Same answer. So which force is going to be the winning forces in which direction? Same answer. Who's winning? It's a bit of a trick question. Who's winning? Look at situation B. Who's winning?
I guess gravity. They both the same.
They both are. Two winners. Look at the picture. If down is winner, look at situation B. Do I have to scroll up? Right? We're talking about this one here, Declan. We just said it's accelerating down. That's the winning direction. Who's winning? Anything pointing down. How many forces are pointing down? They both are. It's like elementary school sports day. No losers, only winners. Okay? So what's my equation going to be here? Gravity and air. So let's step back a little bit further, Ruby. When I say winner minus loser equals M8, what I'm really saying is any forces in the winning direction make those positive. Any forces in the losing direction make those. And we're going to let positive be whatever makes the math easier. In this case, the math is easier to let down be positive. Unlike way back when we did kinematics, we always let down be negative. Here, we're going to do ourselves a favor. Down can be positive. What does winner, no loser. What does winner minus loser always equal? In this case, what does winner plus weak winner equal? MA. Cool. Cool. Alex, what are they asking me to find in example 4? How would I get the A by itself? What's the M doing to the A? What's the M doing to the A right now? So, how will I move it over? We call this Declan's theorem. And here's what we did. We just went, ready? Boom. Boom. Done. That's all. Now, look up. I'm going to erase that. You guys can write it in. But as far as I'm concerned now, for an air resistance question like this, I can ask you one of two questions. I can tell you the air resistance in newtons and say find the acceleration, Declan's theorem divided by m. Or I could have told you the acceleration and said find the magnitude of the air resistance. I think you would minus the mg over and you're good. As far as I'm concerned, both of those are fair game. Okay? But here, definitely. So, A is going to be M2. G, 9.8, plus F air. They told me that, and they told me that in newtons, so I don't need to multiply it by anything. It's just going to be a 5.2 there, divided by 2. You have that one in your head, Mr. Dewitt? Well, maybe. It's going to be 19.6 plus 5 is going to be 24.6, 24.8, 12. No, that can't be right, Mr. Dewick. 12.4? Okay, it was right. Oh yeah, it's bigger than G because gravity and air resistance are both slowing it down. So instead of being slowed down at 9.8, two things are slowing it down, 12.4. Okay. Aryan, let's look at situation C. Which way are we accelerating in situation C? Good. Which way is the winning direction? Same answer. Who's winning? More specific in that picture, which force is winning? Who's losing? And this time it is pointing in the opposite direction. We do have a loser. So there it's going to be winner minus loser equals what? MA. Alex, how am I going to get the A by itself? Good. You way overcomplicated that one last time, didn't you? You know what? You can probably just backspace on your calculator and change the plus sign to a minus sign. Left arrow, probably. Or up arrow. Show me your calculator. Oh, you already did it? So I'll write it out. 2 times 9.8 minus 5.2 all over 2. Do that one in your head. It's going to be 19.6. Take away 5 is 14.6, 14.4, 7.2? Yeah. So now we're being a little more accurate about free fall. 2 units ago, we just always said acceleration negative 9.8 because I think I told you we'll assume everything is in a vacuum. And Diego will still assume everything is in a vacuum this unit unless it says include air resistance. Then you can bring it in. Parachuting is really cool. Have I mentally jumped out of an airplane? Because I have. A 90-kilogram parachutist free falls for a time and then opens a parachute. His new upward acceleration is now 1.5 meters per second squared. Why is his acceleration upwards? Diego, loud and proud. Yes. What direction is the acceleration, Diego? Which direction is my winning force going to be in my free body diagram? Same answer. Same answer. Which way is my longer arrow going to be pointing in my free body diagram? Up. Who's winning? Up. Okay? All that information. You start to see why Newton's law is very powerful if you start to wrap your brain around how they work. Okay. It says draw a free body diagram. You know what? I'm going to label the parachutist right here. What are the forces acting on the parachutist? Get the obvious one. Everybody. Good. What else? This can't be it because he's accelerating upwards. What else? And even though I didn't in this question blatantly say to you, include air resistance, I did when I said he's accelerating up. Okay, so this will be another fair game question to expect you to clue in. Only way to be accelerating up is if there's air resistance. I'll really, really exaggerate it so it stands out. Good. So B said draw a free body diagram. I did. C says write a force equation. Okay, Bryce, who's winning? Who's losing? Equals. Winner minus loser equals what? Good. See? F air minus mg equals ma. In the previous question, I told you air resistance and we found the acceleration. What are they asking me to find, Bryce, in part D? Air. Oh, they want me to get F air by itself. Okay, folks. How will I get F air by itself? Add the mg over? Okay. So in this case, air resistance is going to be ma plus mg. Bryce, they must have told me the mass. Did they tell me the mass somewhere up there? How many kilograms? 90? Good. They must have told me the acceleration. Did they tell me the acceleration somewhere up there as a number? What? 1.2. By the way, starting to see why I also said memorize units, because you knew that was the acceleration because of meters per second squared, right? Is it 1.2? Is that what I said? 1.5. Plus 90 again, and G. And not negative. We took care of that in our winner minus loser stick. Good. What do you get? Oh, I'm going to wait. Bryce is going to type this one into his calculator because he needs to get faster on this calculator, so I need to make him type stuff. Casey's getting a little quicker. You're definitely going to get a positive answer. If you got a negative answer, you've messed up somehow, right? So there's some built-in error checks. If you get a negative answer, probably you picked the wrong winner. Go check your free body diagram. What'd you get? 1,000? 1017? Is that right? Units, it's a force, newtons. Okay. So I wrote here, the force of air resistance is actually not a constant value. It gets larger as speed increases. It gets smaller as speed decreases. The fact that I'm slowing down, a split second later, air resistance will be 1,060, 1,050, 1,014, because I'm slowing down. Eventually, I would reach an equilibrium point where air resistance and gravity were the same size, where the forces were, I'm looking for a word that starts with letter B. Okay. What would my acceleration be then? Joanna, has to be 0. Okay, we have a fancy name for that. When I jumped out of an airplane, when I jumped out of an airplane and I did that classic free fall position, I did eventually stop accelerating. We call that terminal velocity. Your terminal velocity is when air resistance and gravity are the same size. And there's 2 ways that you can do that. Go really fast, like when I was in free fall, or have a big surface area, like when I open my parachute, much smaller terminal velocity, but still a terminal velocity. Put your pencils down, look up.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth.
What are the forces acting on the skydiver right now? Let's do a free body diagram. Get the obvious one. Are they accelerating down? Are they accelerating up? So there has to be a force the same size as gravity pointing up. Oh, that's the surface keeping them from sinking in. What did we call that force yesterday? It was the whole theme of yesterday's lesson. Okay, it was a normal force. So right now, the free body diagram would be mg down, normal force up, same size. Okay? As soon as the skydiver jumps, which force vanishes? The normal force. Free fall, one way to think about it, is the absence of the normal force. That's free fall. So ready?
Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity.
That makes sense. That's Newton's first law. The forces are balanced. You okay with that, Josh? Okay.
Right up until the moment she steps out. Gravity immediately pulls her towards the ground.
Look in the bottom right corner. Notice the velocity. It's increasing. A fancy word for an increasing velocity starts with letter A.
And she starts to accelerate downwards. But air resistance is acting in the opposite direction.
Notice the numbers creep up
faster she
slower and
falls,
slower
the greater the air
as air resistance gets bigger and bigger. There's her terminal velocity. It's right around 55 meters per second for most people. So what are the forces acting on her? Get the obvious one. Gravity. What else? Air. And in this case, right now, at this moment, because the speed has stopped increasing,
the downward force of gravity.
Originally, air resistance
When
was small.
forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating.
55 meters per second. Could someone multiply that by 3.6? How many kilometers per hour is that? Would you want to hit the ground at that speed? No, that would add a different meaning of terminal velocity. It would be very terminal, right? Okay. So how can we increase air resistance? 2 ways. Go faster, that's fatal in this case, or increase the surface area. That's what a parachute does.
She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea.
When she pulls the parachute, which arrow must get bigger? Gravity or air resistance? Why? Because she's going to be slowing. So which means she's accelerating technically in which direction? Which means there's got to be a bigger arrow in which direction? Starting to see Newton's laws tell you an awful lot about what's going on.
To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down.
You can see the meters per second getting slower and slower, but you also see the speed change, decreases
until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea.
Yes, it is. When she hits the ground, that air resistance will be replaced by a normal force. Right at impact, will the normal force be bigger, smaller, or the same size as mg? How do I know? Why must it be bigger? Because when she hits the ground, she's going to be slowing down, which means technically she's going to be accelerating in which direction? She has to accelerate up for a split second. So we should see the normal force get bigger.
As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly. So for skydivers to land safely, they need to understand forces and use air resistance to slow themselves down.
Now, a good skydiver does an extra skill. If you watch really close, what they'll actually do just before impact, they'll slightly change the angle of their parachute to maximize air resistance for a split second. They'll almost try and stall, knowing that they'll drop if they time it wrong, but if they time it just right, they can get that stall right when they're about to hit the ground. That's why you saw some of them land really, really smoothly. That's what my instructor did when he landed with me. We pulled back, we kind of accelerated for a little bit, increased our velocity, and then pulled back to increase air resistance to stall right at impact. That's more complicated. I'm not going to be asking you a question about that, but for what it's worth, that's what's happening. Okay. We can handle, next page, a lot of questions with a good free body diagram, winner minus loser, and not panicking. Example 5. A helicopter accelerates upwards. Which way? That's important. At 2.5 meters per second. What lift force is exerted by the air on the rotors? Okay. Sadie, what's this asking me to find? What? What's it asking me to find, Sadie? What? There's a word, find the word what, and read me the 2 words after it. Second sentence. Psst. What was that? I have no idea what that means, but I'm not going to panic. You know what this might be a good job for? Free body diagram. How do I know? They're asking me a strange force. So, Sadie, let's do our free body diagram right here. Someone wants to put their phone on vibrate. Next year, I'm going to have my Timbits rule back. Next year, if your phone makes a noise, you owe the class Timbits. It's going to be great. Sadie, what are the forces acting on the helicopter? Get the obvious one. Yep. What else? Does it say include air resistance? Well, it kind of says by the air, but wait a minute. What did they call air resistance in this question? They called it something a little bit different. I think lift force. Which way? How do I know which way are we accelerating? Which way does there have to be a bigger unbalanced force? So I'm going to draw F lift, bigger arrow pointing up. So we put all that together. Who's winning? F lift, as we called it in our diagram. Who's losing? Equals. There's my equation. What are they asking me to find, Sadie? Oh, how will they get the F lift by itself? How will I move that over? Yep. Yep. Good. Sadie, what's M? More specific, as a number in this question, what's M? Yep, they told me. What's A? Plus, what's M? 5,500. G, 9.8. How big must the rotor's lift force be for this situation to occur? Do y'all get 67,650? I'll go 67,700. But if you wrote out the whole thing, that's fine. Units, Sadie, it's a force. Yep. Good. Hey, we can do a little rocket science. A rocket which weighs 12,740 newtons on Earth is launched. The force of propulsion is 15,400 newtons. Determine A, the mass of the rocket. How the heck can I find the mass of the rocket? What? Divide what by 9.8? Oh, are you saying that the word weight is another word for mg? Yes, it is. And I'm going to start to say that over and over and do that more and more. I'll give you a weight, not a mass. So I can say, yeah, you know what? Mass is going to be F divided by G. It's going to be 12,740 divided by 9.8. Remember, that mg weight, that's on your formula sheet. No excuse for blanking out on that one. I put that on your formula sheet. 12,740 divided by 9.8. Casey, did you get 1,300 kilograms? Okay. Paul, let's keep going. What does B want me to find? Acceleration. Do you see a VI or a VF or a T or a D or anything like that? Say no. I see forces. You know what? This is going to be a job for a... Yeah. What are the forces acting on this rocket? Get the obvious one. Which way? Yep. And this is kind of weird. mg, I know it's actually 12,740. They gave me that number. What else? Which way is this rocket accelerating? So which way does there have to be a bigger arrow pointing? What force is that? What do we call it? The force of propulsion. I'll call it F prop. And yeah, that is apparently 15,400 newtons. Who's winning? Who's losing? Equals? There you go. What do they want us to find? Ah, Declan's theorem. It's going to be 15,400 minus 12,740 divided by 1,300. A common mistake, kids mistake weight for mass. If this was multiple choice, one of the answers would be if you divided by 12,740, if you treated newtons like kilograms, if you worked for Verizon. Don't be one of those people. I have no idea what the answer is here. Paul, did you get 2.05? 2.061, 2.05? Okay. We can go one step further. So here's some of the physics, the very basic stuff. It was more complicated, but here's some of the physics they had to do for the moon landing. Suppose the rocket is moved to the moon where the acceleration due to gravity is 1.6 meters per second squared, not 9.8. If we want the rocket to accelerate up at 3.5 meters per second squared when it leaves the moon, how much force of propulsion do we need? Sarah, what's this question asking me to find? Of? Okay. Any thoughts on what this might be a good job for? I think so. Sarah, what are the forces acting on this rocket? Get the obvious one. And just so that I don't be sloppy, I'm going to go mg, and I'm going to put a little moon right there to remind myself, don't accidentally, out of habit, put a 9.8 there. Easily preventable. What else? What are they asking me to find? I think F prop. Which way? Bigger, smaller, or the same size as mg, and how do I know? Why? Which way are we accelerating? Which way does the bigger unbalanced force have to be pointing? That's Newton's first. That's the power of Newton's first. I'll exaggerate it so it's obvious. Sarah, who's winning? Who's losing? Equals. What are we trying to get by itself? Sadie, how would I get the F prop by itself? Plus the mg over, right? Good. Going to be ma plus mg. Basically, you'll almost always plus or minus or swappy dance. Those are the three options to get the thing by itself. If you're, and if you're finding A, it's going to be Declan's theorem. All right. M. What was M? Not 1,300. It's the same rocket. A, 3.5 plus 1,300. Ooh, Sarah, not times 9.8, times what? 1.6. If you've ever dove into the moon landings, to leave Earth's gravity, 9.8, massive Saturn V rocket, longer than a football field, huge. To leave the moon, one single tiny rocket, not a three-stage. Why? Smaller gravity. We're going to get a much smaller force of propulsion. Sarah, what'd you get? Type like the wind. 6,000. Is that right? 6630? Compared to 67,700, basically 1/10 as big. Once you're on the moon, it's much easier to get off the moon. Getting to the moon is the challenge. This is why NASA is talking about building a moon base and trying to launch rockets from Mars to the moon. Sorry, to Mars from the moon as opposed to from Earth. We're almost done. We don't always need to do... Oh, Josh, what does FBD stand for? Okay, we don't always need to do a free body diagram. Josh, can you do me a favor, please? Can you read to me example 7? A 1,200 kilogram car, keep going. Yep. The what force? The what force? The what force? If you ever see the phrase net force, you can skip the free body diagram. And the reason is, if you look at your formula sheet, I actually never said F equals ma. I said F net, the net force, equals ma. What I'm saying is I've done the free body diagram already for you, and the numbers that I'm giving you are just once you've gone winner minus loser. So we can go straight to F equals ma. So key idea, when the question asks for the net force, we can go straight to F equals ma, because it's really F net equals ma. Josh, do I know M? Do I know A? What's A? Not yet. Okay? So now I would probably draw a little line and I would say, A equals question mark? What's that 33, Josh? Which one? Yes. What's VI then? How'd you get that? Oh, good old from rest. What's that 8.5? I'm looking for an equation that's got an A, a VI. So all the stuff from kinematics is fair game because A appears in force equations. Looking for an equation that's got an A, a VF, a VI, and a T in it. There is one. Oh, he's getting his formula sheet out finally. Good for him. Get the A by itself, please, Josh. Yeah, it's VF equals VI plus AT. So let's see, what would drop down like a domino? The VF, then what? Divide by T. What else? Minus VI, right? I think you said plus. Minus VI, right? Okay. I mean, I guess, and I wouldn't do this, you could make an argument that there's another force equation that looks like this. I just wouldn't go through the trouble of writing that down or memorizing it. I would argue we can derive it when we need to. Oh, and I heard somebody say, by the way, VI is 0. That's true, so I could actually get away without even writing VI. It's just going to be 33 divided by 8.5. I doubt this will work out nice. This looks like a yucky number. 33 divided by 8.5. Yeah, long decimal. I'm going to write 3.88, but which button am I going to use on my calculator, Josh? Darn right. And then to show this, I'm sticking it over there. I just draw an arrow. That's enough for me to figure out what you're doing. What was the mass? 1,200. What was A? I'm going to write 3.88, but I'm using my answer button. What's the net force? The what force? The net force? 4,660 newtons. 4658.8. I'll go 4,660 newtons. So if you ever see net force, skip the free body diagram, go straight to F equals ma. This next bit is not on a test, but I should point out that everything that I've taught you so far is a lie. Actually, there's only 4 forces in the universe. Normal force does not exist. Air resistance does not exist. Tension does not exist. They're combinations of these 4 forces. What are the 4 forces? There's what we call the strong force. That's what holds the nucleus of an atom together. There's one that we call the weak force. That explains radioactivity. There's gravity, although Einstein would argue gravity is curvature of space-time, not a force. But we're going to be staying within what we call Newtonian physics. We'll treat gravity as a force. And then there's electromagnetism. This explains everything else. And I don't know why I have that video there. I showed you that one a long time ago. I need to update this. What's your homework? 1 is good. 2 is good. So 1 and 2 and 3 are elevator questions where you're standing on a scale. Remember, when you're standing on a scale, which force am I really talking about? The normal force. Okay? 1, 2, 3 is good. 4 is good. 5 is good. 6 is good. So far I've assigned all of them. I know. 7 is good. You can skip 8. 9 is good. 10 is good. 11 is good. 12 is good. These are conceptual questions. 13 is good. Going to skip 14. 15 is good. And 16 is good. I think tomorrow I'm going to press pause. I'm going to give you a take-home quiz, but I'm not going to give you a new assignment. So you'll have tomorrow class to work on this. This is where hopefully it's starting to become a little less confusing and starting to become a little more, okay, I'm seeing how the tug of war works, how the free body diagram works, and how I can use Newton's laws. So you really want to use, there's 15 minutes left in class, you want to use those wisely. You want to use flex if you need to, and tomorrow as well. Okay?